Thank you, Professor Pozzi, for inviting me and giving this opportunity to come to Michigan and see you guys and get exposed to the research you have done here, and hopefully there is in the future will be some potential for collaborations. So today I will talk about gamma ray imaging, specifically about the high purity germanium detectors and one way how we can improve the characteristics or actual response of these detectors in order to get the better quality images. So here's the outline of the presentation, a little bit about the motivation, why we do gamma ray imaging, some basic principles for the gamma ray imaging, or specifically for the Compton imaging, and I will introduce the double-sided segmented strip detectors, the concept of it. Also describe our approach, how to improve the response of these detectors, which is signal decomposition algorithms. And in order to benchmark the response with signal decomposition algorithms, I did some Gen 4 simulations. And then at the end, I will present some experimental results which will show that we are on the right path. So why do we care about gamma rays? People have been asking questions like, what's going on far in the cosmos, or can we look in the side of the body without not being invasive to it, or can we look in the really tiny particles of matter? And it turns out that gamma rays can help us to look at these phenomena, or at least to get closer to these phenomena. For example, the universe is the largest factory of the gamma rays in the cosmos, and doctors are using gamma ray imaging. So we are all familiar with using gamma ray imaging for the treatments and for the verification and for the diagnosis. And the spectroscopy is a great example how we can look at the nucleus and basically identify isotopes. You know, it is not just important to detect gamma rays. It is also important to image gamma rays, because if we are in really harsh background and the background around us is very is variable. So we need to also to have some capability to enhance the position of the source and to be aware where is the source position. And in our group we do two types of gamma ray imaging: Compton imaging, which I will talk more about during the talk, and coded aperture imaging. For coded aperture imaging, I'm pretty sure that you are all familiar with, but just to remind you that we have a gamma ray source, and we have a known pattern, coded aperture pattern, and we have our detector set. Basically, how we get the information about the gamma ray source, we deconvolve our detector response with the known pattern, and we infer the position of the source. And this is the setup. This is our instrument, which I'll talk later about. So Compton imaging has been around for decades, and it was proposed in the early 70s from Schoenfelder, and it was proposed for the astrophysical applications. And actually, he built the instrument and sent it to space, and that's the Compton telescope, Compton telescope. Almost at the same time, it was proposed for biomedical applications. Recently, also, it's a lot of research is going on to try to use the gamma ray imaging for the dose verification, especially proton dose verification. So shooting basically proton beam in the cancer tissue, for example, and imaging gamma rays and trying to correlate the gamma rays with the delivered dose. That's the whole idea. Another good application which has been done in our group recently, we are all familiar with Fukushima accident, and a lot of radioisotopes is now, a lot of radiation is around, and there is this evacuated area, and it's really important to to be able to map this radiation, especially for the areas which are not that not easily accessible. And on this helicopter, we have a device, our device Hemi, which is based on CZT detectors, and it was flown for 27 minutes around this area, above this area, and we looked for the cesium source. And the work was done by Anthony Humphrey's, our group, and actually it was pretty nice result recently obtained in Fukushima. And probably we are all interested in these two applications, nuclear safeguards and nuclear facility verification and homeland security applications. So being able to verify actually what's going on in, for example, an enrichment factory, it's very important. And also preventing some potential nuclear terroristic attacks, it's even more important, especially night and after 9/11. So in all these applications, the whole game is about resolution and efficiency. And our question is really, can we use signal decomposition algorithms to improve one of these parameters? Probably at some point we can do both. Just briefly to introduce, I'm pretty sure that you are familiar with Compton Imaging and the principles for the Compton Imaging. So gamma scatters of one less bounded electron in atom, and it knocks out the electron, and there is a scatter gamma. And this kinematic of this process is very well described. If you assume that the electron is at rest and it's not bounded to the nucleus, which is not true, the process is very well explained by the Compton formula. The theta is a scattering angle of the gamma angle, and E gamma is incident gamma energy, E1 is energy of the scattered photon. Knowing this process, how can we basically do gamma ray imaging? Let's say we have gamma ray source and we have our detector, and the gamma ray interacts within our detector several times. And if you are able to reconstruct the first two interaction positions of the gamma ray within the detector, and to identify the interaction positions and also energies which is deposited in these 2 points, we are able to reconstruct the Compton cone. The axis of the cone is given by direction which connects these two interaction points, and the opening angle is Compton angle. So if you are able to reconstruct several cones from the same source, and overlapping intersection of these cones will give the possible position of the source. That's just naive description of what's going on with Compton imaging. And how we get to the real image in 2D in theta phi space, we basically we put one surrounding sphere around our detector and Compton cone, and this Compton cone now intersects our sphere, surrounding sphere. If we unwrap this sphere in theta phi space, we get something like this. And the source position would be somewhere here. But the world is ideal, and there is no perfect detector. So we cannot determine, if we can determine these interaction positions and energy perfectly, of course, there is no uncertainty. It will still be the cone, but we wouldn't have this thickness on the cone. So cone has finer thickness due to Doppler broadening, because electron is not at rest, and it's bounded to the atom. And also there are uncertainties how we determine the positions of the interaction, and there is finite energy resolution of the detector, which blurs our Compton cone. How we define at this point also I want to introduce two concepts which or two metrics, how we determine the quality of one Compton imager. The first one is angular resolution metric. That's basically resolution of like for any other imaging system, you define the point spread function. Angular resolution metric is basically point spread function for the Compton imager. So let's say we have detector system, we have two reconstructed cones. Angular resolution metric is defined for the known source position. So let's say we know known source position in front of our detectors, and we have a reconstructed cone and reconstructed angle, Compton angle. If we unwrap this in the imaging space, we have something like this. We have these Compton circles, and we have a reconstructed angle and no geometrical angle because we know source position. For each of these cone, we plot the angular resolution metric, and full width half max of this distribution is defined as a angular resolution metric. That's basically how we define the resolution of our system. Another important parameter, like for any imagery, is efficiency. And how we define imaging efficiency. Let's say we have this arm distribution, and we have a certain spectrum in our detector, and we want to image photopeak events, because we are sure that these events are fully deposited in our detector, and they are most likely belong to our source, not to the background. And the ratio between these two values, so counts which fall in the full width half maximum of arm distribution, and counts which fall in our photopeak, that's what defines our efficiency. So these are basic principles. Now let me introduce the high purity germanium detectors, double-sided segmented. So as you probably noticed, for the gamma ray imaging, we need to determine the position of interaction. So we need to somehow to code the space where interaction happen. And therefore we use segmented detectors. But what are the basic, what's the basic principles behind the semiconductor or high purity germanium or silicon detectors? They are basically inverse biased p-n junctions diodes, and there is no free mobile charge in it. And when gamma comes, it creates charge, electron and holes, and there is high electric field across the detector, which basically drift this charge to the electrodes. And we basically measure the charge of this, which arrives at the electrodes, in order to create charge in within the detector. The energy required to create the charge is 2.96 eV. So, basically the number of carriers which you get in your detector is energy deposited divided by this number. But as I said, we need to code the space where interaction happened in order to know where is the interaction point. Therefore, we use segmented detectors. And these detectors are produced in the Lawrence Berkeley National Lab by Mark Kaman and Steve Bucks. So we have electrodes on the, it's not anymore one electrode on the side. It's 38 electrodes on one side and 38 electrons on the other side. And they are orthogonally oriented. That is how we basically coded the 2D space. And it has 38 strips, 2 millimeter pitch, and 0.25 millimeter gap size. 15 millimeter thickness, which is really great. With germanium, you can make them bigger and be really efficient with them. And this is some great parameters for the energy resolution. It's 3.5 kV. It can be better, but this is what is the current status of our system. Okay, so gamma comes to our detector, and it deposits certain energy. And let's say we can just trigger one strip on one side and one strip on the other side. And that's the simple case. And you say, okay, I'll put interaction in the middle of it. I know which energy which I collected at the electrodes, and that's all what I care about. But what if we have, and usually we will see that this is the large number of events where we have several strips fired on one side and several strips on the other side. The uncertainty becomes 6 millimeters in this case, and 4 millimeters in the other case. So, and as you remember from the previously, that really affects the quality of our image. Can we reduce this uncertainty? And the answer will give us a signal decomposition algorithm. And really, the charge, when it travels to the electrodes, it is shared between their electrodes, so you actually don't know what's the exact energy of interaction and how many interactions do you have within this space. So these are all type of questions which need to be answered in order to fully reconstruct the gamma ray path. Here is some just example in one of our data sets what kind of events we can get in our detector. So it's basically 40% of these simple events, 1-1 events. 1-2 events I called when you have one strip on one side and two strips on the other side fired. So it's basically for the rest of them, 64%. We need some more clever algorithm to resolve and to increase the efficiency of our system. But we'll see that we'll also, with our algorithm, increase the resolution of the system. As I said, how we determine simple approach, and it has been implemented in NCT Compton telescope, which is developed in Lawrence Berkeley lab. So and they just use these single events, but they have 10 detectors, and they can sacrifice efficiency because they have a large number of material there. So and they use these 1-1 events for the XY, and it turns out that the signal, the difference between the arriving times of electrode and of electrons and holes signals at the electrodes is sensitive to the depth. So we can calibrate this difference to the depth, and that's how we infer the depth of interaction. So we have three coordinates, x, y, and z. And this is one example how it can be calibrated. Of course, when you get to close to the contacts, you have some kind of non-linearity. But can we do better than this? And we need to do better than this, especially in our case. And it turns out that physics gives us that opportunity. So we have created charge. When charge travels to the electrode, it also induces, you have, for example, one collecting electrode. But when charge travels to the electrode, it also induces a charge, image charge on the neighboring strips. And it turns out that these signals are also sensitive to the interaction point. So we are going to use these signals to reduce the uncertainty where interaction happens. For example, so these are examples of the signals collected on these three electrodes. So charge collecting electrons and neighboring strip electrodes, let's say. And these are the transients. So this is the collecting signal, and these are transients on the neighboring strips. And for example, just simple approach, comparing these amplitudes, or ratio between these two signals, amplitudes of these two signals, you can do certain calibration and move your interaction point close to the strip which has a higher amplitude. And that is also that's implemented in our group. We'll see later some results from that approach as well. But why don't use the whole signal if you already have saved them? And even more, it's very often that you have two interactions. Even in the simple case, if you have 1-1 event, so one strip on one side and one strip on the other side, we have two interactions which are really close to each other, which in any other algorithm you cannot resolve that. And usually with a simple approach, you would put your interaction in the middle of these two, which will screw up your direction of your cone or tilt it a little bit and bring additional noise to your image. So, and this is a good example of what's going on when you have two interactions. So you have this signal, which is probably from one of them, and another on top of it, and we have these imaging charges on the neighboring strips. If we are able to handle these events, we will definitely increase efficiency and reduce uncertainty as well. So, and this is just a simulation done with console, which shows us that also these neighboring strip events and also the collecting charge signals, they are sensitive to the depth. So what is plotted here? In the middle of this strip, we took 5 points and simulated the signals for the different depth of interaction. And you see that there is definitely, even just being the same energy, but different image charges and different rising time. That's obvious from the depth. You have different rise time. So that's the whole idea, which I mentioned. So you have field calculations for your detector. You have a non-source, you have non-interaction position and energy, and based on that, you calculate the signals for the, now by just calculating these 5 points, let's cover the whole detector with these points and calculate the detector response. And based on this using, so in field calculations, you use the electrostatics model, you calculate weighting fields, potentials, you calculate the velocity of the carriers, and based on that, you get simulated signal basis. You have on the other side, you have collected signals, waveforms, and using signal decomposition algorithms, you infer X, Y, Z, and energy. And here is a nice example how it works. This is, so the red one is fitted and the blue one is experimental signal. Let's try this experimentally. What is plotted here? We have a slit collimator and we have a cesium source in front of it. And we are going to see how fine we can resolve these interaction points within one strip. So moving this source for 200 micrometers within one strip, so that's basically 10 steps, we are trying to resolve these distributions, selecting the energy, those events which belongs to the Compton edge, because they are most likely one signal interaction. And it turns out that the uncertainty of 500 micrometers, which is 0.5, which is 4 times better than what is originally 2 millimeters, is inbuilt resolution of our system. We can reconstruct the position of the beam inside of the strip. Let's try this for the several steps. And these are 7 of them, which is basically how many you get. Because other 3 or 2 belongs to the gap, and the gap is getting has its own story. I think there was a student here at University of Michigan who did this, is just analyzing these events from the gap. Jason Howard, he's now a professor somewhere. So, and we can see that we have resolved the whole pattern, moving the source. And this is the nice example from the ones at the edges of the strip and one in the middle. So we can now claim definitely that we can resolve the position within uncertainty of 500 micrometers. Okay, so in order to say and to verify also algorithm in terms of imaging, we did some giant force simulations just to see what can we expect with certain uncertainties in terms of position and energy, and also including Doppler broadening, to see what can we expect from our system and where we fit with our recent results. So this is our system. Compact, we called it compact Compton imager. It has 2 of these high purity germanium detectors. And it has another systems like LiDAR scanner for just to getting panoramic view, panoramic camera, and preamplifiers, which reads these signals from the electrodes, and these signals goes to the digitizers. Again, 38 strips. This is the detection error, closer look. And what we simulated in Giant 4 is just having source, far field, 8 feet from the detectors, and having these 2 detectors, 2 basically germanium bulks, recording these gammas or trying to detect them. And here is what we've done. So with Giant 4, what Giant 4 provides to us is simulated position and energy of interactions. We blur these position and energies according to the experimental observations, and based on the algorithm, because we know source position, we can reconstruct the R, angular resolution metric. And here is some results. So if we have perfect system, no blurring, just from Doppler broadening, just that fact that, and that's the physical limit of the system, we will get 1.25 resolution degrees for the system. If you blur position and if we increase another extra blurring in energy of 3 kV and blurring positions with 0.5 millimeters in each direction, X, Y, and Z, we will get 2.15. For 1 millimeter is 3, And these are some results for the different kind of, including, of course, what you expect and what you can infer from this is that just 0.5 millimeter it brings another degree of uncertainty in your image, or it screws up your resolution. And some experimental results to see where we are. So the same setup, having cesium source in front of the detectors, and what we best get is 3 degrees, selecting these events which are 1-1 events. So just trying to have the cleanest set what we have, and to try what we get, and it is between something 0.5 and 1 millimeters compared to the simulation. And this is comparison for with the parametric approach, which I also talked about. So this is one image just to show how it looks like with these events, 1-1 events, 3 degrees. And this is parametric approach, and basically it doubles efficiency, and for the whole events it's basically better 3 degrees compared to the parametric approach. And okay, this is the summary. So definitely using signal decomposition algorithms, we are able to reach the sub-millimeter resolution of the system. We can increase the efficiency, and we can definitely improve the resolution of the system. And this is also a nice result. So comparing for different uncertainties, these two parametric approach and signal decomposition approach. So this is what I talk about 3 and 5, but we have also other points. So definitely constant increase in efficiency and constant increase in resolution compared to the SPEAR is a parametric approach. So, and this approach has been published by Lucia Mihailescu from our group. So the signal decomposition is really great thing. It combines mathematical methods and whatever we know about the physics, what's going on in the detector, and it's the way to go with these detectors if you don't have enough money to build with 10 detectors or whatever, and you want to increase your efficiency and resolution as well, which will be important for something which recently has been proposed to image the small mouse in front of the system. So having mouse with cesium, just injected the cesium in it, and to see how biological system behaves with cesium, because this cesium which comes from Fukushima, we just wanted to understand what's going on. So, but that started actually too late for me in the late October, and these are some results also from Ross Barnowski from our group, which tries to reconstruct the 3D scene with this system, and trying to overlap gamma ray image on top of it, and to just get feeling in 3D where is the source. At this point, I also want to thank my advisor Kai Vetter and Jasmina Vujic, just great people, and I really for 4 years have been experienced such great things from them at UC Berkeley. These are guys who did also a tremendous job in terms of modeling, Dan Cheevers, Julian Rochel, and Brian Plumley. And this is nice view. This is Berkeley. This is Berkeley Lab. For those of you who have visited, you know how is it great. And this is our group, pretty large group. A lot of gamma ray imaging and detector development. And when I started, I was probably it was like 5, 6 of us, and now it's in 5 years. It's growing, thanks to the wonderful people which guide us.
Great.
Thank you.
Thank you very much.
Yeah.
All societies are become more and more developed, and so that means more agriculture, more industry, and more contamination. And so these contaminants are getting into the water supplies.